The purpose of a grounding electrode system, often abbreviated as GES, on the secondary side of a transformer installed within a building is multifaceted, but primarily it's designed to provide a low resistance path to ground for fault currents and lightning currents. This low impedance path is critical for ensuring electrical safety and preventing damage to equipment in the building structure. The primary reason for this grounding system is to protect people and property from electrical shock and fire hazards. When a fault occurs, such as a short circuit, the fault current needs a safe and effective path to return to the source, which in this case is the transformer. A properly installed GES provides this path. Without it, fault currents can flow through unintended paths, such as through a person touching a faulty appliance, leading to severe electrical shock or electrocution. Moreover, high fault currents can generate excessive heat, potentially igniting nearby flammable materials and causing a fire. The supply-side grounding electrode system is connected to the secondary side GS through the transformer's grounding conductor. This grounding conductor plays a vital role in maintaining a common ground reference between the primary and secondary sides of the transformer. This connection ensures that any voltage potential differences between the two sides are minimized, which is essential for safety and proper equipment operation. The size of this grounding conductor is typically determined based on the requirements outlined in the National Electrical Code, or NEC. The NEC specifies that the grounding conductor must be sized adequately to carry the maximum fault current that could reasonably be expected to flow through it. This sizing is crucial because an undersized grounding conductor may not be able to handle the fault current, leading to its overheating and potential failure, thereby compromising the effectiveness of the entire grounding system. The secondary side GES is also connected to the building's structural steel, if the building has it, and to the metal water piping system within the building. These connections are strategically made to ensure that all conductive surfaces within the building are at or near the same electrical potential. By bonding these metallic elements together, the risk of electrical shock is significantly reduced. Imagine a scenario where a fault occurs and a metal enclosure becomes energized. If the enclosure is not properly grounded, a person touching it could become part of the fault current path, resulting in a dangerous electric shock. However, if the enclosure is bonded to the GS, the fault current will flow through the grounding system, tripping the circuit breaker or fuse and quickly de-energizing the circuit, thus preventing the electric shock. In the event of a fault, the fault current will flow through the grounding conductor and the secondary side GES to ground. This flow of current is what triggers the overcurrent protection devices, such as circuit breakers or fuses, to operate and interrupt the circuit. When a fault occurs, the voltage on the secondary side of the transformer may rise temporarily. However, the GES helps to limit this voltage rise to a safe level. This voltage limiting action is important because excessive voltage can damage sensitive electronic equipment and pose a risk to personnel. The GES provides a low impedance path for the fault current, which helps to stabilize the voltage and prevent it from reaching dangerous levels. The GES also serves as a critical protective measure against lightning strikes. Lightning strikes can introduce extremely high voltage surges into electrical systems, potentially causing severe damage to equipment and posing a significant fire hazard. The GES provides a low resistance path to ground for these lightning currents, diverting them away from sensitive equipment and safely dissipating them into the earth. This helps to protect the transformer, connected equipment, and the building's electrical system from the destructive effects of lightning. The size of the secondary side GES is determined by several factors, including the size of the transformer, the type of building in which it is installed, and the specific grounding requirements outlined in the NEC. The NEC provides detailed tables and guidelines that electrical engineers and installers use to determine the appropriate size of the grounding electrodes and grounding conductors. These tables take into account the transformer's capacity and the building's characteristics to ensure that the GES is adequate for the specific application. To further elaborate on the components and installation practices of a secondary side grounding electrode system, it's important to understand the different types of grounding electrodes that can be used. Firstly, a ground rod is a common type of grounding electrode, typically made of copper or copper-clad steel. It is driven into the earth to provide a direct connection to ground. The NEC specifies the minimum length and diameter of ground rods, as well as the required depth to which they must be driven. Secondly, a ground ring is another type of grounding electrode consisting of a bare copper conductor that is buried in a continuous loop around the perimeter of the building. Ground rings are often used in areas with high soil resistivity, where a single ground rod may not provide an adequate ground connection. Thirdly, a concrete encased electrode, also known as a UFA ground, is a grounding electrode that is encased in concrete. This type of electrode is typically installed during the construction of a building, and it provides a very effective ground connection due to the large surface area of contact with the earth. In addition to the grounding electrodes, the grounding electrode conductor, or GEC, is another essential component of the GES. The GEC connects the grounding electrode to the transformer's neutral point or the equipment grounding bus. The size of the GEC is determined by the size of the transformer's secondary conductors, as specified in the NEC. Proper installation techniques are crucial for ensuring the effectiveness of the GES. All connections must be made using approved methods and materials such as exothermic welds or listed connectors. The grounding electrodes must be installed in locations that are readily accessible for inspection and maintenance. The grounding conductors must be protected from physical damage and securely fastened to the grounding electrodes and equipment. Now let's delve deeper into the role of the GES in limiting voltage rise during fault conditions. When a fault occurs, the fault current flows through the grounding system, creating a voltage drop across the impedance of the grounding path. This voltage drop is known as ground potential rise, or GPR. The GES is designed to minimize the GPR by providing a low impedance path for the fault current to return to the source. The lower the impedance of the grounding system, the lower the GPR will be. A low GPR is important for protecting personnel and equipment from dangerous voltage levels. If the GPR is too high, it can create a significant voltage difference between the grounded surfaces and the surrounding earth, potentially leading to electric shock hazards. Furthermore, a high GPR can damage sensitive electronic equipment connected to the electrical system. The GES also plays a critical role in mitigating the effects of lightning strikes. Lightning strikes can inject massive amounts of energy into electrical systems, causing severe damage and posing a significant fire hazard. The GES provides a low impedance path for the lightning current to flow to ground, diverting it away from sensitive equipment and the building structure. This helps to protect the transformer, connected equipment, and the building from the destructive forces of lightning. To ensure the effectiveness of the GES in protecting against lightning strikes, it's important to install lightning arresters or surge protective devices, SPDs, at the service entrance and at other strategic locations within the electrical system. These devices help to divert lightning surges to ground, further reducing the risk of damage. The NEC provides specific requirements for the installation of lightning protection systems, including the size and type of grounding conductors, the spacing of grounding electrodes, and the bonding of metallic component. Now let's discuss some of the common misconceptions about grounding electrode systems. One common misconception is that the GES is only necessary for large buildings or industrial facilities. In reality, every building with an electrical system needs a properly installed GES to ensure the safety of occupants and the protection of equipment. Another misconception is that the supply-side grounding is sufficient and that a secondary-side GES is not necessary. While the supply-side grounding is important, it does not provide the same level of protection as a dedicated secondary-side GES. The secondary-side GES provides a localized ground reference for the transformer and the connected equipment, which helps to minimize voltage rise and protect against lightning strikes. Another misconception is that the size of the grounding electrode conductor, GEC, is not critical. In fact, the size of the GEC is crucial for ensuring that the GES can effectively carry fault currents and lightning currents. An undersized GEC can overheat and fail, compromising the effectiveness of the entire grounding system. Now, let's move on to the inspection and maintenance of grounding electrode systems. Regular inspection and maintenance are essential for ensuring that the GES remains effective over time. The grounding electrodes and grounding conductor should be visually inspected for signs of corrosion, damage, or loose connections. The resistance of the grounding system should be measured periodically to ensure that it is within acceptable limits. The NEC recommends that the resistance to ground should not exceed 25 ohms. If the resistance is higher than 25 ohms, additional grounding electrodes may need to be installed to improve the grounding system. Any damaged or corroded component should be replaced immediately. Loose connections should be tightened to ensure a good electrical connection. The grounding system should be inspected and tested after any significant electrical work is performed on the building. It is also recommended to inspect the grounding system annually, especially in areas with corrosive soil conditions. In conclusion, the grounding electrode system on the secondary side of a transformer installed within a building is a critical safety feature that provides a low-resistance path to ground for fault currents and lightning currents. It protects people and property from electrical shock and fire. The GES is connected to the supply-side grounding system and to the building's structural steel and metal water piping system to ensure that all conductive surfaces are at the same electrical potential. The size of the GES is determined by the size of the transformer and the type of building in which it is installed. Regular inspection and maintenance are essential for ensuring that the GES remains effective over time. The grounding electrode system is a vital component of any electrical system, and it should be properly designed, installed, and maintained to ensure the safety of occupants and the protection of equipment. The National Electrical Code, NEC, provides comprehensive guidelines for grounding and bonding, and it is essential to follow these guidelines to ensure a safe and effective electrical system.